Good morning. For this week material, the main objective is to learn very well how the logistic equation motivation comes to be. So we're going to learn the logistic equation as an improvement of the exponential differential equation. And then we will talk about in more details how typical infectious disease is modeled, in particular the contact rate. And then we finish with a very simple, perhaps one of the most basic examples of an exponential, of an epidemic model that is essentially a version of the logistic equation. So the main goal for this week is to not only learn about some basics of how you model an infectious disease, in particular the contact rate, but more importantly, how to view fundamental equations like the logistic equation in different contexts. So that will be extremely important for the for our course, to recognize the same math in different contexts. It will take a little bit of effort in the beginning, but it should get easier if you put the effort in understanding. It'll be very easy later on to pinpoint the math property that you would recognize immediately, regardless of the story behind the problem, so regardless of the context, the real life context of the problem. So assuming you went through the notes that you're supposed to do, those of you who are my students and taking this class for the summer, you know already that we talked about the exponential OD as one of the simplest possible population models, right? So let's say, again, as usual, P of t is the number of people at time t, so just a demographic model, but we'll talk about epidemics later. Then the exponential OD, it's p prime equals some constant rate times p. And then the solution is going to be p of t equals p naught e to the rt. And remember, the index 0 throughout the course, unless otherwise specified, will always denote the initial population. All of these models will have an initial population size. Therefore, we won't have just differential equations, but we have also initial conditions attached to them. So I went into greater details in the notes about the problems with the exponential ODE. Is that one of the main issues is that while they are easier mathematically, obviously they become quickly unrealistic as time goes on. So they can only be useful for a limited range of time if you want to model something that happens in reality. As time goes on, if R is positive, then the population increases to infinity at ever-increasing rates, and then the size becomes unrealistically high of the total population. So two outcomes, right, for the long-term behavior of the population. So either P of t goes to infinity, unrealistically so, again, as t is big enough, if R is greater than 0, and then the population goes to 0 if R is less than 0. So because R is the growth rate, this is easy to understand why that might be the case, right? The difference between the birth and the death. If it's positive, then the population increases. If it's negative, it goes to 0. So the logistic model comes with an improvement of this problem here, of the fact that the population should increase to infinity pretty much in any circumstance. We're not going to get into too much details right now to justify the situations, various situations that will cap the population growth. But it's easy to understand that no matter what population you're talking about, whether you talk about human population or animal population or plants, whatever, at some point, limited resources, and I'm using this word very generally, so limited resources should stop the population growth at some point, or should limit the growth of P of t. So something has to happen in the model to indicate that the population cannot grow indefinitely. For various reasons, limited food, limited resources, maybe even space, physical space. I mean, now not for the people, for the human populations, but even if you imagine that the resources are plentiful, there is at some point a finite amount of space in an environment, and obviously that should limit the population growth. Now, while the population growth should be limited, obviously how much is that upper limit depends on the situation, and that may change from time to time. So obviously, for instance, in the case of human populations, modern agriculture means you can produce more food cheaply. So obviously that upper limit right now probably is bigger, not probably, for sure is bigger than it used to be in the past when the food production was much less efficient. So how do you do this mathematically? The easiest thing in the logistic case is to basically make the growth rate, and that, by the way, that's not the only way to do it. So make the growth rate decrease with the population size. That's one basic example that we are going to study, because again, and I'll mention this more often, things can go far more complicated than that. For example, if the population is low, actually the growth rate may actually accelerate with the population size, because the opportunity for reproduction becomes more efficient if more individuals come into contact. In ecological models, you will see this assumption called the Lee effect, which we might talk about it later. And then you can make more complicated functions here to, in fact, make that growth rate decrease only if the population size gets really big, so that the limited resources will be will have an effect at that moment, because those limited resources won't have much of an effect if the population is small. But remember, we built this theory in this class from easier examples to slightly more complicated. So it's going to be an upward scale, so to speak. And for now, we're going to focus on just this main assumption. Let's make the growth rate decrease with the population size. So therefore, you can imagine that equation, instead of having a constant, so pay attention here, instead of a constant, you also have some factor here in the growth rate. So the per capita growth rate, the stuff that's multiplied by p, imagine you have an extra function that indicates this logistic effect. So this f of p will be decreasing with the population p. So the sky's the limit in terms of how many types of functions you can come up with. One of the easier ones is to make this function linear. So basically a decreasing line, a decreasing linear function in P. And again, there's no limit on how you can write this. One of the standard ways of writing this equation is to have this decreasing linear function in the form of 1 minus P over some constant K. Now, at this point, I want you to, again, remember to force yourself all the time to remember what is the actual function of t, because for convenience, we don't write p of t all the time. So what stands for the dependent variable, or the function with respect to t, and what are the constants? So r is a constant, and k, in this case, actually, it's a positive constant. The reason it's positive is because you'll see this becomes, in the case of a positive growth rate, this becomes actually the upper limit of the total population. So, and again, I want to mention here, and we'll talk about that in this part, or maybe the second part, there's no reason to have this form here, this parenthesis in that form. You could, for example, have a constant here, not 1 minus a constant times p. So you can have these various constants in different positions. The important thing is to have a decreasing linear in p, and of course the population p over here. Okay, so this is the logistic growth rate, the stuff multiplied by p. And at this point, it might be useful to run this with d field to see how it looks like. But we could do this actually by hand. We could do the phase line stability analysis. if we set the right-hand side equal to 0, we're going to have two equilibrium points, P1 equals 0, and from setting 1 minus P over K equals 0, we get P2 equals K. So two equilibrium points with a phase line. I'm going to actually write two of them because I want to show you what happens if the growth rate R is positive and if R is negative. Because, you know, R could still signify, like before, the difference between the natural birth and the natural death rate. And you could think of 1 minus P over K, just the logistic effect, namely just the effect of the population size for resources. In other words, as P goes big, I mean, as P is increasing, this quantity essentially reduces the growth rate. So if R is greater than 0, if you look at the sign table carefully, if I start with a population P greater than K, so this equilibrium here is K and this is 0, K and 0. So if I start with something greater than K, then I have a fraction greater than 1 here. So 1 minus something greater than 1 makes the parenthesis negative. Now everything else is positive. So if I start above K, the population decreases toward K. If I start between 0 and K, this parenthesis becomes positive. And if I start with something below 0, which we want to do, I'll talk about that immediately, but if we start with something less than 0, then the population, I mean, I'm not going to call it population, obviously, but P of t goes to minus infinity. So, I mean, it's going to decrease. So this will be unstable point, 0, and this K will be stable. Now, if R is less than 0, all the signs will be reversed. Okay, so if you start above K, it goes up. If you start between 0 and K, it goes down. If you start below 0, it goes up. So 0 becomes stable, and then K becomes unstable. So it is time, well, let's actually write down the result first of all, and then we'll continue with the discussion. So if R is greater than 0, P of t approaches K if P naught is greater than 0, and P of t approaches minus infinity, right? It goes to minus infinity if P naught is less than 0. All right, what happens to the other part if R is less than 0? P of t approaches 0, the population approaches 0. If you look carefully here, if 0 less than P naught less than K, so if you start basically, well, not only that, but, well, let's just leave it at that. So if P naught is between 0 and K, and if P naught is less than 0. Right, so if I start basically anywhere below K, I approach 0. If you start above K, so if P naught is greater than K, P naught goes to infinity. P of t goes to infinity. All right, so it's time now to actually obviously disregard the results or the math basically that has no relevance in real life. So in other words, there is no point in looking what happens to the model if the initial population is less than 0, if P naught is less than 0. So the math equation tells you that P of t goes to minus infinity if P naught is less than 0, but obviously there's no such thing as a negative population. So you will never use the model, obviously, with an initial population size less than 0. In other words, we pretty much do not care what happens if one starts with a population below 0. That's why actually in the second case here, when R is less than 0, I put here P naught between 0 and K, because this is the part that actually really matters. not the part when P naught is less than 0. Now, what's left, sometimes even the population above K, and even when you start above K, sometimes that's disregarded. Now, it's true that we can start with a population greater than K, but really in most of the demographic models involving the logistic equation, K really is an upper limit in the sense that, you know, you run the model and you have a population that essentially is really growing and didn't really exhaust all the limited resources, right? So, I mean, it presumably started from low values, and then if things go well, it goes up. If things go bad, it goes down. But pretty much you never really imagine a situation where you actually go above K. I suppose an example in which you would start above K is to say you have an island, let's say, that can sustain 1,000 individuals of a certain species. So you know that that island cannot actually hold more than 1,000 individuals of that population, and then you parachute in a second, you know, in a day, 5,000 individuals. And so therefore, from the beginning, the population will go down, and it will probably settle at the at this upper limit. So except situations like that, for the most part, most of the realistic ranges for the initial population size are between 0 and K in the logistic model. That's why you'll see sometimes the graph only shown between 0 and K in some of the models. And in the notes, I actually gave you the explicit solution if the population is between 0 and K, which I'm going to write on the second part immediately. So bottom line, the logistic model says if I have some increase in growth rate positive, so if the difference between the birth and the death rate is positive, then the population doesn't grow indefinitely, but it will settle to a limiting point here, to the positive equilibrium point, which is called also the carrying capacity, because of this interpretation of kind of the upper limit of the population given the resources provided. So let's continue with this analysis in the second part.